Today we're determining the surface area of a three-dimensional lava droplet consisting of cubes on a 3D grid. Here you can see an example. Okay, so first of course we have to parse, that's the usual stuff, and then we put the result into a hash set, so we can use it as an efficient lookup function. Then a helper function for the neighbors of a cube, so the cube xyz has of course two neighbors on the x-axis, two neighbors on the y-axis, and two neighbors on the z-axis that only differ by 1. Then for part 1, the question is, or the exercise is count up all the sides that aren't connected to another cube. So we can literally translate this English into Clojure. First we pass the droplet, and then for every cube in the droplet and all their neighbors, we only keep those neighbors when they are not part of the droplet. So here we use the hash set as a function. And then we count them all up, of course. And that's already all there is to it, part 1. For example, here that's 10 because this cube has 6 surface areas, this one has 6 surface areas, 2 of them touch, so 5 plus 5 is 10. Right, then for part 2, we compute the exterior surface, because in part 1 we could have counted interior surfaces if there were air bubbles in the lava droplet, of course, right? So we have to do it with a more involved approach. I chose a flood fill in 3 dimensions, a breadth first search or breadth first flood fill. Okay, so yeah, maybe let's start here. So first we pass our droplet again, and then we determine the minimum and maximum coordinates of our 3-dimensional volume that we have to flood fill. So the droplet is a set of 3-element vectors, and here with a cat transducer we flatten those vectors. So now we can work with just the numbers, and we determine the minimum starting with the maximum value and the maximum starting with the minimum value. And then we decrement the minimum and increment the maximum just to ensure that we can walk around our lava droplet in all 3 dimensions and not be blocked anywhere. Okay, and this helper function simply determines for a given cube if x, y, and z all are within the minimum maximum that we just computed. Okay, and then a little helper function, not droplet, that's basically the opposite of droplet. So droplet is a hash set. Complement of droplet is not a hash set, that's just a function. So if we look at complement, we simply negate the function result, right? So that's all there is to it, and that will become useful later on. Then how do we start our 3-dimensional flood fill? So the border hash set contains all the cubes from where we're going to explore next. Initially, that's just in a corner of our determined volume. And the visited hash set will become larger and larger. Initially, it's just the border where we have already been. And then surface is initially 0. Okay, so if the border is empty, if there's nothing left to explore, then surface holds the final result. Otherwise, we actually have to do work. So what exactly do we have to do? So again, we loop through all the cubes in our border and all their neighbors as usual, and only keep the neighbors when 2 condition holds, namely the neighbor has to be within the bounds, otherwise we will just walk off into infinity, and we haven't visited the neighbor yet, otherwise we would just bounce back and forth. Okay, and this for comprehension can contain the same number or the same neighbor multiple times when it is reachable from multiple positions. And that's the good thing, because we want to count all the surfaces if they are reachable from different positions. So we simply filter the cubes in the border by, are they part of the droplet? And if so, we have just reached that droplet. We count all of those and then add them up to the surface. Okay, and then here we filter for the opposite. That's where the not droplet comes in. So only the cubes in our border that are not part of the droplet we want to put into a new hash set. So that's where we're going to explore from next. And then we recur and put the new border into the visited set. Yeah, that's already everything. So this is a breadth first search. Works quite well, nice functional approach. Initially, I did it with a recursive depth first search, but the problem is for the example where we have 8 in every dimension, 8 to the power of 3 is 512. That worked quite well. with up to 500 stack frames. But here we have 24, and 24 to the power of 3 is about 15,000, and that's too much for the JVM stack. If you try a depth first search on the JVM, you will simply blow your stack.